We're going to look at solving trigonometric equations here in this section. Chances are this will be a multi-video section because there's lots of different styles, lots of different types, lots of variation when it comes to solving trig equations. And my personal opinion is it's one of the most important things to learn in a trigonometry class, okay? We're going to rely on the unit circle, we're going to rely on identities, and we need to be able to identify all solutions and solutions in specific intervals. So first things first, let's just get a picture here of what it is that we're looking for when we're solving. So we're going to start with simple equations. The first one we're looking at is the cosine of theta is equal to 1/2. Now, if we think about our unit circle, and hopefully, I don't think I have it here, but I'm going to generate it quick. My unit circle has a cosine value of 1/2 right here and right here. Remember, generally, we can quickly generate the unit circle. Everything is over 2, so 1, why won't it go? 1 over 2, root 3 over 2 here. It's root 2 over 2, root 2 over 2 here, root 3 over 2, 1 over 2. So 1, 2, 3, 1, 2, 3. Down here, same thing, 1 over 2, negative root 3 over 2, root 2 over 2, negative root 2 over 2, root 3 over 2, negative 1/2. And that's just quadrants 1 and 4. We would have on our unit circle the same things, just reflections and different sign values in quadrants 2 and 3. Okay, so where do we have a cosine value of 1/2? That happens here, and that happens here. Okay, if you have a unit circle, you should get that out when you're working with problems that involve solving, so that you can quick reference if you don't have it mentally memorized at this point. So what angles is that? This happens when theta is, well, that's a pi over 3, the top one. The bottom one is, you can say negative pi over 3, or I'm going to choose to say 5 pi over 3, or in other words, 5/3 pi. Okay, now here's what I want us to keep in mind. That's not every single solution. That's not every possible solution. That's just 2. Wouldn't it make sense that if you had gone all the way around and then landed there again, right? So you had gone your original pi over 3, and then from that moment you went a full circle, you would land at that same spot, producing a cosine value of 1/2. So any full cycle later would also land you at that spot. We're going to put a k behind here, and we're going to say where k is an integer. Okay, that means you could go from this spot now, another full cycle later, land there, and that would also be a cosine value of a positive 1/2, right? So like we already established 7/3 pi, 13/3 pi, and we could just keep going around, full cycle, full cycle, full cycle, full cycle. The same thing happens with the one that's down here, right? You went all the way around, sorry, let's start with, you're at 5/3, and you go all the way around one time, you will be at 11/3 pi. The cosine value is 1/2. If you go all the way around again, you will land there again, and the cosine value is 1/2. So both of these would generate all the solutions, okay? Now, negative k values also work. So if I'm here and I back up one full cycle, I would land at a negative pi over 3, and the cosine of negative pi over 3 is also a positive 1/2. So where k is an integer, we don't say positive, we don't say negative, we just say k is an integer, which implies it's positive or negative. This are all the solutions with only 2 L's. Okay? Let's try it again. Find all possible exact solutions for the equation sine of t is equal to 1/2. So where is sine 1/2? Again, hopefully you're thinking about your unit circle and you see that the sine produces a 1/2 here and here. Where is that? Where is that happening? Well, that happens at pi over 6 and at 5 pi over 6, right? Now, those are not the only spots where this happens, because if I'm here at pi over 6 and I go one full cycle around, I also land there, and I would get a sine value of 1/2. Same thing for 5 pi over 6 and any full cycle later. These are all solutions. Okay, and now you got the basic gist of it. So we are going to go and make the equations a little bit more intense, more algebraic, more stuff going on. Okay, we're going to look at number 17 here. Example number 17, and there's a couple different approaches that we could take with solving this trigonometric equation. One is we could take cosine of 2x and we could replace it using our double angle formula, or we can talk about just what 2x could equal. So if the cosine of this angle, and if I temporarily call it alpha, the cosine of alpha equals a positive 1/2, well, this means that alpha here or here, right? Based on our unit circle, I know that this means that alpha is equal to pi over 3 plus any full cycle, any number of times, so plus 2 pi k later. Another alpha is, I could say negative pi over 3, or I could say 5 pi over 3, whichever, plus any full cycle thereafter. Now, it really wasn't alpha, so let's think about what that meant for our original problem. This was really 2x that equaled that, and 2x that equaled that, which means then I need to divide both of these by 2. And the reason I'm doing that is so that I get x by itself. First one, if I divide by 2, I have to divide everything by 2. Same thing here. So that means that this is going to become pi over 6 plus 1 pi k. And the bottom one is going to become 5 pi over 6 plus 1 pi k. And I don't need to write the 1. And this would be all solutions, okay? Now, it's asking for the solutions in this interval from 0 to 2 pi. So now is when I do my k values. So if k equals 0, the first one will be pi over 6. The second one will be 5 pi over 6. If k equals 1, we have, for the top one, we have pi over 6 plus 6 pi, right? So I would get 7 6 pi. If k equals 1 for the next one, I would have 5/6 pi plus 6/6 pi, 4 and 11/6 pi. I can already see that if k is a 2, here I'd be adding, top one I'd be adding a 2 pi, resulting in a too big of a number. The second one, same thing. The only thing I should check is that if I plug in a -1, I would get pi over 6 minus 6/6 pi. That will be a -5/6 pi, so that's outside of the region of interest. Here I would get 5/6 pi minus 6/6 pi. That would give me -1/6 pi, also also negative and outside my window of interest. So for this particular problem, there are 4 solutions that fit the interval of interest that they're asking for. So for this next one, I'm going to add 3. I'm going to isolate my trig function, basically, if I can. So cosine of theta will equal, and there was a 2. Why is my stuff erasing? Come on. Cosine of theta is equal to -2 when I add the 3, right? There's a 2 here still. And then divide by 2. We get -2 over 2. In other words, cosine of theta is equal to -1. And now I'm thinking about my unit circle. Where does cosine of theta equal -1? And that happens right here and only there, right? So this is going to be when theta is equal to pi plus any full cycle later. Now, this is all solutions. They are asking us, by putting this on the end, they're asking us for only the solutions from 0 to 2 pi. Well, I can see when we get more complicated with our equations, we're going to put in different k values. If k is a 0, for this equation, we will get pi. If k is a 1, we're going to get 3 pi. Well, that's greater than what we want, so we're out. That one we're not going to count. We should probably also look in the negative region. When k is a -1, and do the math on there, we'll get a negative pi. Well, that's below our region of interest, so we don't want that one either. So the only answer for this problem that they're looking for is just pi, okay?